Jupiter is about 365 million miles away at its closest point to Earth. And if you ask how long it would take to get there, the answer you'll find most often is somewhere between 2 and 6 years. People read that, nod, file it away, and move on. A number got stated. The question feels answered. But that range, 2 to 6 years, is one of the most misleading summaries in all of popular science, because every number inside it is technically correct and almost completely useless without context. What spacecraft? Launched when? Does it need to slow down when it gets there? Or is it allowed to just blow past? Is the crew biological? Or is it a machine that doesn't care how long the trip takes? The answer changes dramatically depending on every single one of those questions, and most people have never been asked any of them. Here is what makes this worth paying attention to. Jupiter is not just a big planet sitting out there in the dark. It is the largest object in the solar system after the Sun itself. It has at least 95 known moons. Some of those moons are bigger than the planet Mercury. One of them, Europa, has a liquid ocean buried under its ice, an ocean that contains more water than every ocean on Earth combined. And the scientific community considers it one of the most promising places in the entire solar system to look for life. We have sent exactly a handful of spacecraft to Jupiter in all of human history. A handful. The first one arrived in 1973. Given what might be waiting out there, the fact that we've barely looked is extraordinary. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. And yet for all of that, the travel time question still gets flattened into a single shrug of a number. 2 to 6 years. As if the difference between 2 years and 6 years is a rounding error. As if the reasons behind that difference don't reveal something genuinely strange about how space travel actually works. The real story is not a number. It is a set of trade-offs that spacecraft engineers lose sleep over, and those trade-offs explain why some missions race to Jupiter in just over a year, while others take the long way around and arrive half a decade later. The New Horizons spacecraft reached Jupiter in 13 months. The Galileo spacecraft took 6 years. Both of those statements are true. They describe journeys to the same planet. The difference between them is not luck or budget. It is physics, timing, orbital mechanics, and one fundamental question: did the spacecraft need to stop? Because in space, slowing down is just as hard as speeding up, and the fuel cost of breaking into orbit around Jupiter is enormous. New Horizons didn't break. It flew through the Jovian system like a bullet through an open window and kept going. Galileo had to stop, and stopping required a different kind of journey entirely. Slower, longer, stranger, looping back past Venus and Earth twice before it had enough speed to make the trip work at all. None of this gets explained when someone says 2 to 6 years. None of it gets explained when a headline says, "We could reach Jupiter in under 2 years." Every one of those claims is sitting on top of a set of assumptions that the headline never mentions. The real answer depends on a set of questions most people have never been asked. And the moment you start asking them, the journey to Jupiter gets a lot stranger. The first thing to understand about traveling to Jupiter is that the distance between Earth and Jupiter right now is not the same as it was last year, and it will not be the same next year. This is not a minor variation. The difference between Jupiter at its closest and Jupiter at its farthest is nearly 240 million miles. That is more than twice the distance from Earth to the Sun. When people give you a single number for how far away Jupiter is, they are averaging across a moving target. And that average hides something that matters enormously the moment you try to actually go there. Here is the picture. Earth orbits the Sun once every 365 days. Jupiter orbits the Sun once every 11.86 Earth years. Both orbits are elliptical, which means neither planet traces a perfect circle. They speed up when they are closer to the Sun and slow down when they are farther away. Earth moves much faster, completing nearly 12 full orbits for every single orbit Jupiter completes. So the gap between the two planets is constantly opening and closing, never steady, never fixed, running through its full range on a cycle that repeats roughly every 13 months. At their closest point, when Earth swings between the Sun and Jupiter in what astronomers call an opposition, the two planets are about 365 million miles apart. That is the number people tend to reach for when they talk about the distance to Jupiter, because it is the smallest number and it sounds the most reachable. At their farthest point, when Jupiter is on the opposite side of the Sun from Earth, that gap stretches out to about 601 million miles. The average across the full range of orbital positions works out to roughly 444 million miles. Every one of those numbers is technically correct. Every one of them tells a different story about how long the journey takes. Think about the Moon for a second. The Moon is not perfectly fixed in distance either, but its variation is small enough that when you are planning a mission, it barely registers as a complication. Apollo crews launched, flew a predictable path, and arrived. The geometry was never going to dramatically betray them. Jupiter is nothing like that. Jupiter is a target sliding steadily across the solar system, and whether you catch it close or catch it far changes your travel time by years, not days. Miss the optimal window, and you are not dealing with a minor inconvenience. You are dealing with a fundamentally different mission. This is where the synodic period comes in. The synodic period is the time it takes for Earth and Jupiter to return to the same relative position, and for Jupiter, that number is 398.88 days, just a little over 13 months. What this means practically is that the favorable launch window for a mission to Jupiter opens roughly once every 13 months. The geometry lines up, the distance is manageable, and mission planners have a chance to send a spacecraft on an efficient path. Then the window closes. Then you wait, not a few weeks, not a month, more than a year before the next reasonable opportunity arrives. Were you planning a mission and something went wrong on the pad? A faulty sensor, a software problem, an unexpected weather delay. If that delay pushes you past the launch window by even a few weeks, the orbital geometry has already started working against you. The path that was efficient becomes expensive. You either burn dramatically more fuel to compensate, accept a much longer journey, or wait 13 months and try again. Space agencies have faced this exact scenario. It is not theoretical. The solar system does not hold the window open while the paperwork catches up. Jupiter's slow crawl around the Sun is part of why this matters so much. Earth is quick. We tear through one full orbit in a year. Jupiter is almost stationary by comparison, grinding through its 11.86-year journey around the Sun so slowly that from our perspective, it barely moves against the background of distant stars. Each year, Jupiter advances roughly 30 degrees along its orbital path. Earth laps it again and again. From the surface of Earth, Jupiter appears to drift slowly across the sky over months and years, rising earlier each night, eventually reaching opposition where it is closest and brightest, then falling back toward the sun in our sky, before emerging again on the other side. What this means for mission timing is that the geometry is always in motion, and the calculations for where Jupiter will be when a spacecraft actually arrives are not simple. You are not aiming at where Jupiter is today. You are aiming at where Jupiter will be in 2, 3, 5 years, depending on which path you choose. Get the math wrong and you miss, not by a little, by hundreds of millions of miles. There is another layer to this. At the closest approach distance of 365 million miles, a radio signal traveling at the speed of light takes about 33 minutes to reach Jupiter. At the farthest distance of 601 million miles, that same signal takes about 53 minutes. Right now, depending on where Jupiter sits in its orbit, those numbers are somewhere in between. The distance is not just a travel time problem, it is a communication problem, a planning problem, and a fuel problem, all compressed into one number that changes every single day. Here is something worth holding in mind. When the Galileo spacecraft was launched in 1989, mission designers knew they were dealing with a moving target. They didn't aim at Jupiter's position on launch day. They aimed at a point in space where Jupiter would be 6 years later, after Galileo had looped through the inner solar system collecting speed from Venus and Earth. The spacecraft flew away from Jupiter at first, toward Venus, back past Earth, out again. All of it precisely calculated around the fact that Jupiter is never where you left it. The window problem compounds in a way that is almost cruel for anything involving a crew. A robotic spacecraft can launch, coast for years, and arrive without anyone aboard suffering for the delay. Humans don't work that way. Every day added to the journey is a day of radiation exposure, food consumption, psychological strain, and bone density loss. So the launch window is not just a scheduling concern. For a crewed mission, the launch window is a hard constraint tied directly to crew survival. The difference between launching at the optimal moment and launching a month late is not just a math problem, it is a human cost. So when someone tells you Jupiter is 365 million miles away, or 444 million miles, or 601 million miles, understand that they are not wrong. They are just describing a single frame of a film that never stops running. The planet is always somewhere in that range, always moving, and the distance on the day you launch is only one part of the calculation. Before you can calculate how long the trip takes, you have to know when you're leaving. And the answer to that question changes everything that comes after it. The obvious way to reach Jupiter would be to point a spacecraft at it and fire the engines until you get there, and that approach would fail almost immediately. Here is the problem. Jupiter is not sitting still waiting for you. It is moving at roughly 29,000 miles per hour around the Sun, tracing a path that takes nearly 12 Earth years to complete. Earth is moving too, at about 67,000 miles per hour in its own tighter orbit. By the time any spacecraft you launch today has crossed hundreds of millions of miles of empty space, Jupiter will be somewhere completely different than where it was when you left. If you aim directly at Jupiter's position on launch day, your spacecraft would arrive at an empty patch of space roughly where Jupiter used to be. The planet would be long gone. This is not a small error. We are talking about a miss of tens of millions of miles. So the real calculation is not where is Jupiter now. It is where will Jupiter be in 2 years, or 3, or 5, depending on how fast your spacecraft is moving and what path it takes. You are not shooting at a target. You are leading a target, the way a hunter leads a moving animal rather than firing where it stands. Except in this case, the animal is 89,000 miles wide, moving at 29,000 miles per hour, and your bullet takes years to arrive. Get the math slightly wrong, and you miss by a distance that dwarfs the entire inner solar system. Now here is where it gets stranger. Once you have figured out the right direction, you cannot simply accelerate toward Jupiter and coast, because in space, there is no friction, no air resistance, nothing to push against. On Earth, if you throw a ball, it eventually slows down and falls. In the vacuum between planets, a spacecraft moving at 40,000 miles per hour will keep moving at 40,000 miles per hour essentially forever, unless something acts on it. That sounds like an advantage. In some ways, it is. But it also means that whatever velocity your spacecraft has when it approaches Jupiter is the velocity it will still be carrying. If you want to stop there or enter orbit, you have to kill that velocity yourself. There is no atmosphere to drag against, no runway to roll down. You have to your engines in reverse and burn fuel to slow down, the same way you burned fuel to speed up. Slowing down costs exactly as much energy as speeding up. People don't think about this. They imagine getting to Jupiter as the hard part and arriving as the easy part. It is the opposite of easy. Getting captured by Jupiter's gravity in a controlled way, rather than swinging past it and flying off into the outer solar system, requires a massive engine burn at exactly the right moment. That burn costs fuel. That fuel has to be carried the entire way from Earth. Which brings us to the most brutal constraint in all of rocketry. Fuel has mass. Mass requires fuel to accelerate, which means the fuel you need to carry also needs fuel to carry it, which means that fuel needs even more fuel. It spirals. This is the tyranny of the rocket equation, worked out by a Russian schoolteacher named Konstantin Tsiolkovsky in the 19th century, and it has not gotten any kinder since. The equation tells you exactly how much fuel you need to change your velocity by a given amount, and the answer is always more than you want it to be. Want to go twice as fast? You don't need twice the fuel. You need exponentially more, because every extra pound of fuel you load onto a spacecraft is a pound that itself requires fuel to accelerate, and that fuel requires fuel, and the loop keeps tightening. Think about what this means practically. A spacecraft designed to reach Jupiter and enter orbit needs to carry fuel for the initial burnout of Earth orbit, fuel for any course corrections along the way, fuel for the braking burn at Jupiter, and fuel for everything that comes after. All of that fuel sits on the spacecraft from the moment of launch. The rocket that lifts it off the pad is not just carrying a spacecraft. It is carrying a spacecraft plus years' worth of propellant, and the sheer mass of that propellant requires even more fuel just to get off the ground. This is why interplanetary spacecraft are mostly fuel. The science instruments, the computers, the structure itself, those are a small fraction of what actually launches. The rest is propellant, sitting there, waiting to be burned. What this means for speed is counterintuitive. Going faster requires more fuel. More fuel means more mass. More mass means your engines have to work harder. Your engines working harder burns through that fuel faster, which changes your trajectory. Every decision compounds. And because there is no margin for error across hundreds of millions of miles, small mistakes in the initial calculation do not stay small. They grow. A trajectory error of a fraction of a degree on departure becomes a miss of thousands of miles by arrival. A fuel budget that runs thin before the braking burn means the spacecraft sails past Jupiter with nothing to stop it. The distances involved punish imprecision in ways that have no equivalent on Earth. This is why the engineers who design interplanetary missions spend years on trajectories before a single component is built. The path matters as much as the spacecraft. The timing matters as much as the engine. And none of it can be fixed once the vehicle leaves the pad. Everything about getting to Jupiter comes back to this. Speed is not free, direction is not simple, and the math punishes every mistake without warning. In 1925, a German engineer named Walter Hohmann worked out the most fuel-efficient way to move a spacecraft between two planetary orbits. The answer he arrived at has governed interplanetary mission design ever since. Hohmann wasn't working with computers. He was working with mathematics, pencil, paper, and what he discovered was elegant in the way that only genuinely correct things are elegant. His insight was this: the cheapest way to move from one circular orbit to another is not to fight the geometry. It's to use the geometry. You give the spacecraft one single push to stretch its orbit outward into an ellipse. Let it coast all the way to the far end of that ellipse, where the target planet's orbit is. Then give it one final push to circularize again. 2 burns. Everything in between is free. The spacecraft is simply falling through space along a path that the laws of gravity already laid out. It costs nothing beyond those 2 moments of thrust. Picture Earth's orbit as a circle sitting close to the Sun. Jupiter's orbit as a much larger circle sitting far out. The Hohmann transfer is an ellipse that just barely kisses Earth's orbit on one side and just barely kisses Jupiter's orbit on the other. The spacecraft starts at the kiss point near Earth, fires its engine once to leave Earth's orbit and begin the long arc outward, then coasts for the entire crossing until it reaches the kiss point near Jupiter. If it wants to stop there rather than fly on past, it fires again to slow down and match Jupiter's orbit. If it doesn't need to stop, it can skip that second burn entirely. The whole thing is almost mathematical poetry. It is the minimum possible energy expenditure to bridge 2 orbits. Nothing cheaper exists, but cheap energy has a price, and the price is time. A Hohmann transfer from Earth to Jupiter takes approximately 2.73 years. Nearly 3 years of coasting through the dark, with the engines off. Carried along by nothing except the orbital arc Hohmann calculated a century ago. For comparison, the Moon is a 3-day trip. Mars, on a Hohmann transfer, takes roughly 9 months. Jupiter is in a different category entirely. You're not talking about a long flight. You're talking about years. This is why the Hohmann transfer sets a floor, not a ceiling. It's the slowest fuel-efficient option, and it's also the minimum energy option, and those 2 things are connected. You cannot have one without the other. If you want to go faster, you have to burn more fuel. You have to push the spacecraft onto a more aggressive trajectory, a steeper ellipse, one that cuts across to Jupiter's orbit faster, but costs significantly more propellant to achieve. That trade-off is always sitting in the background of every interplanetary mission. Speed and fuel are in constant negotiation. The Hohmann transfer is the point on that curve where fuel consumption is lowest and travel time is longest. Now, actual missions rarely follow a pure Hohmann transfer. There are several reasons for this. One is timing. A true Hohmann transfer requires the planets to be positioned in a very specific relationship when you launch, so that Jupiter will be at the far kiss point of your ellipse exactly when your spacecraft arrives there. If the planetary geometry isn't favorable for a pure Hohmann path, mission designers have to modify the trajectory. That usually means accepting either higher fuel costs or a longer journey. Sometimes both. Another reason missions deviate is gravity assists. If a spacecraft can swing past Venus or loop back past Earth before heading out to Jupiter, it can pick up extra velocity from those planetary flybys without burning a drop of additional fuel. The route becomes longer in distance, sometimes dramatically longer, but the spacecraft arrives with more speed than a direct path would have given it. It used less propellant to get there. That seems like a contradiction until you understand what's happening. The spacecraft is stealing orbital energy from the planets it passes. That is a trick the Hohmann transfer doesn't use at all. We'll get into how that works in detail later. For now, the important thing is that gravity assists are one of the main reasons real mission trajectories look nothing like the clean ellipse Hohmann drew. There's also the question of what the mission needs to do when it arrives. A spacecraft that only needs to fly past Jupiter can skip the second engine burn entirely and keep all that fuel as velocity. That makes a significant difference. The burn required to actually enter orbit around Jupiter is enormous. This was because Jupiter's gravity is enormous. Cancelling out enough speed to get captured by that gravity demands a long, powerful engine firing at exactly the right moment. A flyby probe carries none of that burden. It just keeps going. So when people ask why some spacecraft reach Jupiter faster than others, part of the answer is almost always that the faster ones didn't stop. What Hohmann's transfer gives you then is a baseline to measure everything against. It is the reference point that mission designers start from before they start making trade-offs. Any spacecraft using conventional chemical propulsion on a direct path, aiming to arrive at Jupiter with any kind of control over what happens when it gets there, is working within the constraints Hohmann described. The physics haven't changed in 100 years. The rockets are more powerful. The computers are vastly more sophisticated. The trajectory analysis is extraordinarily refined. But the underlying math is the same math Hohmann worked out by hand in 1925. Every mission you'll hear about in the sections ahead, from the first clumsy flybys to the most sophisticated orbiters, was designed with Hohmann's curve somewhere in the background of the calculations. Sometimes the mission followed it closely. Sometimes it departed from it dramatically. But it was always the starting point, always the thing being improved upon or deviated from, always the floor of what was possible. The Hohmann transfer gives you the floor. No spacecraft using conventional chemical propulsion and a direct efficient route can reach Jupiter faster than about 2.5 years. Most take considerably longer. Pioneer 10 launched in March of 1972 and became the first spacecraft ever to cross the asteroid belt, which at the time was considered one of the most uncertain parts of the entire mission. Nobody had sent anything through it before. Nobody actually knew what was on the other side. The asteroid belt had a reputation that, it turns out, was somewhat undeserved. Popular imagination pictured a dense, churning field of tumbling rock, the kind of thing you see in a movie where a pilot has to dodge and weave just to survive. Scientists were more measured than that, but even they weren't sure. Some estimated the debris density might be high enough to puncture a spacecraft moving at tens of thousands of miles per hour. There was genuine uncertainty about whether Pioneer 10 would make it through intact, or whether it would be shredded before it ever got close to Jupiter. It made it through without a scratch. The asteroid belt, as Pioneer 10 revealed, is mostly empty. The rocks are real, but they're spread across a band of space so vast that running into one by chance is almost vanishingly unlikely. This was not a small discovery. It was the thing that opened the outer solar system to exploration. Before Pioneer 10, the belt was a psychological barrier as much as a physical one. After Pioneer 10, it was just a region you crossed. That single data point changed the calculus of every outer solar system mission that came after it. Now, about the timeline. Pioneer 10 launched in March of 1972. It reached Jupiter in December of 1973. That's roughly 21 months from launch to Jupiter. Pioneer 11 followed in April of 1973 and arrived at Jupiter in December of 1974. Again, about 21 months. What's striking about those numbers is that they don't fit neatly into the Hohmann transfer picture. The minimum energy path takes closer to 2.5 years. Pioneer was faster than that. How? The spacecraft were moving quickly. Pioneer 10 hit a peak speed of around 82,000 miles per hour. That kind of speed costs fuel, and it means the spacecraft arrived before Jupiter had fully traveled to the intercept point that a slow minimum energy trajectory would have used. You pay for the extra speed with propellant, but you bank it as time. Were these missions perfect? No. The instruments were simple by modern standards. The cameras were primitive. The telemetry was slow. But what Pioneer returned was extraordinary for its era. Jupiter was enormous in ways the numbers hadn't prepared anyone for. The Great Red Spot was a real, persistent structure in the cloud bands. The radiation environment around Jupiter was punishing, far more intense than engineers had expected, and it nearly overwhelmed Pioneer 10's instruments during closest approach. That was a warning nobody had been prepared for. The radiation belts of Jupiter turned out to be among the most hostile environments in the entire solar system, and Pioneer got the first real measurement of just how hostile they were. Pioneer 11 used what Pioneer 10 had learned. Engineers adjusted its closest approach trajectory so it wouldn't take as severe a radiation hit. Pioneer 11 also flew by Jupiter on a different path, which gave it a gravitational kick that sent it on a trajectory towards Saturn, the first spacecraft ever aimed at that planet. Jupiter wasn't the destination. Jupiter was the fuel station. And that's the part worth sitting with for a moment. Both Pioneers arrived at Jupiter after 21 months, which sounds like a success story for fast travel. But neither one slowed down. Neither one attempted to enter orbit. They came screaming in at tens of thousands of miles per hour, made their closest pass, collected what data their instruments could grab in the hours around approach, and then Jupiter's gravity bent their paths and flung them outward. Pioneer 10 was eventually aimed at the star Aldebaran. Pioneer 11 headed toward the constellation Aquila. Both of them are still out there. We lost contact with Pioneer 10 in 2003, somewhere around 80 astronomical units from the Sun. Pioneer 11 went silent in 1995. They're drifting now, dark and cold, carrying a gold plaque etched with a drawing of a man and a woman and a diagram of where Earth is in the galaxy, just in case someone finds them. Here is what the Pioneer missions actually proved when you strip it down. Getting to Jupiter in under 2 years is possible with mid-1970s technology. Crossing the asteroid belt is survivable. Jupiter's radiation environment is brutal and will kill your electronics if you're not careful. And flying past a planet while using its gravity to redirect your trajectory is a workable, elegant solution to the problem of not having enough fuel to do what you want to do. What Pioneer did not prove is that you can get to Jupiter and stay there. The 21-month timeline is real, but it comes with an asterisk the size of the spacecraft itself. That clock was running for a flyby, not an orbital insertion. Slowing down enough to be captured by Jupiter's gravity requires burning a massive amount of fuel at precisely the right moment, and the spacecraft that did it later had to carry all that extra propellant, which made them heavier, which changed the math entirely. Neither Pioneer stopped at Jupiter. They used it as a slingshot and kept going, which is a distinction that matters enormously when you're trying to understand what reaching Jupiter actually requires. Voyager 1 and Voyager 2 launched in the summer and fall of 1977, and both were aimed at Jupiter, not because Jupiter was the destination, but because Jupiter was the door. To understand why, you have to go back to something that was figured out in the late 1960s by a graduate student named Gary Flandreau, working at NASA's Jet Propulsion Laboratory. Flandreau was running calculations on planetary positions when he noticed something remarkable. In the late 1970s, Jupiter, Saturn, Uranus, and Neptune were going to line up in a configuration that only happens once every 175 years. A spacecraft launched at exactly the right time could use each planet's gravity to slingshot to the next one, collecting speed at every stop. The whole outer solar system, reachable in a single mission. NASA called it the Grand Tour, and the window for it would close and not reopen until the year 2153. If they didn't go then, nobody alive today would ever get another chance. 2 spacecraft were built. Voyager 2 launched first on August 20th, 1977, on a trajectory designed to take full advantage of the alignment. Jupiter, then Saturn, then Uranus, then Neptune, each planet handing the spacecraft off to the next. Voyager 1 launched about 2 weeks later on September 5th, and here is where the mission gets interesting. Voyager 1 was not aimed at the Grand Tour. Engineers deliberately put it on a faster, more aggressive path to Jupiter and Saturn, one that would get it to the planets sooner, but bend it away from Uranus and Neptune entirely. The trade-off was speed. Voyager 1 reached Jupiter in March of 1979, roughly 18 months after launch. Voyager 2 arrived the following July, about 23 months out. Same solar system, 2 different clocks, because trajectory is everything. What they found at Jupiter shook the people reading the data. Jupiter was not what anyone expected. The Great Red Spot, which astronomers had been watching through telescopes for over 3 centuries, turned out to be a storm so vast and so violent that 2 Earths could fit inside it. It had been spinning for longer than recorded history. The cloud bands that look like decorative stripes from Earth were actually hurricane-force jet streams running in opposite directions at hundreds of miles per hour. The whole planet was churning, layered, and alive in ways that no telescope had ever made clear. Then there were the moons. The 4 large Galilean moons, Io, Europa, Ganymede, and Callisto, had always been known as points of light. Up close, they were worlds. Europa showed a surface cracked like a broken eggshell, smooth and young, which told scientists the ice was being resurfaced continuously from below. That was a clue that took years to fully interpret, but the implication was hard to ignore. Something liquid might be moving under that ice. Ganymede turned out to be the largest moon in the entire solar system, bigger than the planet Mercury. Callisto was ancient and cratered, a record of 4 billion years of impacts sitting perfectly preserved. And then there was Io. Io was expected to be a battered, dead rock. What Voyager found instead became one of the most dramatic moments in the history of planetary science. A navigation engineer named Linda Morabito was examining an image of Io when she noticed something on the edge of the moon, a faint umbrella-shaped plume rising off the surface. She almost dismissed it. She didn't. It was a volcanic eruption, actively happening, captured mid-blast by a camera traveling at tens of thousands of miles per hour. Io was the most volcanically active body in the solar system. Nobody had predicted it. The data said otherwise, and the data won. Voyager 1 used Jupiter's gravity to bend towards Saturn, arriving there in November of 1980. During the Saturn flyby, engineers aimed Voyager 1 at Titan, Saturn's large moon, which required a specific approach geometry. That geometry kicked Voyager 1 out of the plane of the solar system entirely, ending any possibility of further planetary encounters. It didn't matter. The Saturn data alone was worth the sacrifice. Voyager 2 continued on its grand tour path, reaching Saturn in 1981, Uranus in 1986, and Neptune in 1989. No spacecraft has visited Uranus or Neptune since. What the Voyager missions demonstrated, beyond all the science, was a lesson in how to use the solar system itself as infrastructure. Every gravity assist is a transaction. The spacecraft arrives with a certain speed relative to the planet, swings through the gravitational field in precisely the right geometry, and leaves with more speed than it came in with. The planet loses a nearly immeasurable fraction of its own orbital momentum. The spacecraft gains thousands of miles per hour for free. Without Jupiter's assist, neither Voyager would have reached the outer solar system on any practical timeline. With it, Voyager 2 crossed the entire outer solar system in about 12 years, a journey that would have taken decades on a direct path using the rockets available at the time. Both spacecraft crossed the heliopause, the boundary where the sun's influence gives way to interstellar space. Voyager 1 in 2012 and Voyager 2 in 2018. They are the only human-made objects that have ever left the solar system. They carry golden records with sounds and images from Earth, encoded for any hypothetical reader who might find them in the distant future. Their nuclear power sources are fading, transmissions are growing weaker, but the motion never stops. Both spacecraft are still moving today, carrying the momentum Jupiter gave them in 1979, traveling farther from the Sun than any object humanity has ever sent into space. Galileo launched from the Space Shuttle Atlantis in October of 1989 and didn't reach Jupiter until December of 1995. And the reason for that 6-year journey is one of the clearest illustrations of how orbital mechanics actually work in practice. The Voyagers had the luxury of speed because speed was the point. Their payloads were relatively light, their trajectories were optimized for a planetary grand tour, and neither one was asked to stop. Galileo was asked to stop. It was the first spacecraft ever designed to enter orbit around Jupiter, and that single requirement changed everything about how the mission had to be built. Entering orbit means carrying enough fuel to brake. Braking fuel is mass. Mass requires a more powerful launch. And here is where the problem started. The space shuttle, paired with the upper stage available in 1989, simply could not throw Galileo directly to Jupiter. The numbers didn't work. The spacecraft was too heavy, and the rocket wasn't strong enough to give it the velocity it needed for a direct path. So the mission designers did something that sounds almost absurd the first time you hear it. They sent Galileo the long way around. The route went like this. First, a flyby of Venus, then a swing back past Earth, then another swing past Earth again. 3 planetary flybys in the inner solar system, each one stealing a small piece of that planet's orbital momentum and transferring it to Galileo, building up speed the launch vehicle couldn't provide. This technique is called a Venus-Earth-Earth gravity assist, and it is exactly as complicated as it sounds. The spacecraft looped through the inner solar system for years before it had accumulated enough velocity to head outward. By the time Galileo finally broke free and pointed itself at Jupiter, it had covered roughly 2.4 billion miles. Jupiter, at its farthest point from Earth, is about 600 million miles away. Galileo traveled 4 times the maximum possible straight line, a distance to reach its destination. Think about that. A road trip where the only route available requires looping through 3 other states twice before the highway opens. The journey took 6 years and 2 months, and nobody considered this a failure. It was the only way to get there. Don't lose sight of this detail. During that 6-year cruise, Galileo wasn't idle. It made scientific observations on every flyby. When it swept past the asteroid Gaspra in 1991, it became the first spacecraft to photograph an asteroid up close. When it passed asteroid Ida in 1993, it discovered that Ida had its own small moon, a tiny rocky companion nobody had known existed. These were bonus discoveries, captured during a journey that was, itself, a detour. The science had already begun before Galileo ever reached its destination. Then, in July of 1994, something extraordinary happened while Galileo was still in transit. Comet Shoemaker-Levy 9 broke apart, and its fragments slammed into Jupiter one after another over 6 days. Every telescope on Earth watched the impacts from the front. Galileo watched from behind. It was the only instrument in the solar system positioned to see the actual collision side directly. The data it captured was irreplaceable. A spacecraft not yet at its destination, already witnessing something no other machine in history could observe. When Galileo finally arrived at Jupiter in December of 1995, it did not arrive alone. 5 months earlier, mission controllers had released an atmospheric probe, a separate, hardened capsule on a collision course with Jupiter's cloud tops. That probe hit the atmosphere at about 106,000 miles per hour. The deceleration was brutal. In the first 2 minutes, it shed 99% of its velocity. Heat shields absorbed the energy of entry. Temperatures reached 15,500 degrees Celsius, hotter than the surface of the sun. And then the probe survived. A parachute deployed. Instruments came online. For 58 minutes, it transmitted data from inside Jupiter's atmosphere. pressure readings, temperature measurements, wind speeds, chemical composition, before the pressure and heat finally crushed it. 58 minutes. The probe we sent to Jupiter's atmosphere lasted less than an hour, and in that time, it fundamentally changed what we knew about the planet. Wind speeds were far higher than models predicted. The chemical composition was different from what solar system formation theories expected. Helium was scarcer than anticipated. The data raised as many questions as it answered, which is usually how the best science works. Meanwhile, the main spacecraft entered orbit. What followed was nearly 8 years of continuous Jupiter science. Galileo completed 35 orbits around the Jovian system, making close passes at each of the 4 large moons. Io showed active volcanoes more powerful than anything on Earth, mountains taller than Everest, lava lakes, a surface being continuously remade. Europa revealed a cracked, icy crust floating above what appeared to be a liquid ocean, and that single finding redirected decades of planetary science toward a question that is still unanswered. Is there something alive in there? Ganymede turned out to have its own magnetic field, the only moon in the solar system known to generate one. Callisto's ancient cratered surface looked frozen in time, undisturbed for billions of years. None of this would have been possible with a flyby. A flyby gives you hours at most, a brief, brilliant snapshot as the spacecraft hurtles past and keeps going. Galileo had years. It could watch Io's volcanoes change between passes. It could refine its measurements of Europa's ocean with each successive orbit. It could notice things that only reveal themselves over time. The difference between Galileo and everything that came before it was the difference between a photograph and a documentary. In 2003, mission controllers deliberately crashed Galileo into Jupiter. Its power was fading, its instruments aging, and there was concern that an uncontrolled end might eventually contaminate Europa, the moon scientists most wanted to protect for future investigation. The spacecraft that had taken 6 years to arrive met its end in seconds. Galileo spent nearly 8 years studying Jupiter from orbit and returned more data about the Jovian system than everything before it combined. But it took 6 years just to get there, and that trade-off was not optional. New Horizons launched on January 19, 2006, and reached Jupiter in just over 13 months, a record for any spacecraft to make that journey. And the reason it could move that fast comes down to one specific decision that shaped everything about the mission. That decision was simple. New Horizons was never going to stop. Galileo took 6 years to reach Jupiter because it needed to slow down enough to be captured into orbit. Fuel for braking, mass from fuel, more fuel to move that mass. That loop compounds brutally every time you add weight. New Horizons was freed from all of it. It had one job: get to Pluto before Pluto's atmosphere froze out. Pluto drifts on a long, strange orbit that carries it far enough from the Sun that its thin nitrogen atmosphere collapses and freezes against the surface for decades at a time. There was a window. Miss the window, and the scientific mission you designed the spacecraft around becomes a very expensive photograph of a frozen rock. Speed was not optional for New Horizons. It was the entire point. So engineers built the spacecraft around velocity in a way nobody had done before for a mission like this. New Horizons weighed about 1,054 pounds fully loaded, which is light for a deep space probe. Its science instruments were carefully selected. Nothing extra. Nothing that added mass without a clear return. The spacecraft was essentially an arrow, stripped down, balanced for distance, pointed outward. And to launch it, NASA used the Atlas 5551, one of the most powerful configurations available at the time. When New Horizons cleared Earth's gravitational pull, it was moving at roughly 36,400 miles per hour. No human-made object had ever left Earth that fast. Here is something that demands your attention. That speed alone, 36,400 miles per hour, would not have been enough to reach Jupiter in 13 months. That's where Jupiter comes in, not as a destination, as a tool. New Horizons was aimed at Jupiter with a very specific geometry, designed to thread the spacecraft close enough to the planet to steal velocity from it. Jupiter's gravity grabbed the spacecraft, pulled it through a slingshot arc, and flung it outward with significantly more speed than it arrived with. At closest approach to Jupiter, New Horizons was moving at roughly 52,000 miles per hour. The Jupiter flyby had added around 9,000 miles per hour to its speed without burning a single drop of fuel. That extra velocity would carry it across the remaining distance to Pluto, another 3 billion miles, in a time frame that actually made the mission viable. Jupiter was not a waypoint, it was the engine. The flyby itself lasted only a matter of hours at closest approach, but the science team had planned it carefully. New Horizons wasn't just passing through, it collected measurements of Jupiter's atmosphere, observed the Great Red Spot, studied the plasma environment around the planet, and got its first close look at some of the Galilean moons. It watched Io and caught volcanic activity in progress. Even at the speed it was moving, even with only hours in the neighborhood, the spacecraft returned useful data. But that data was secondary. What mattered was the trajectory, and the trajectory worked exactly as designed. The difference between New Horizons and every other spacecraft that had visited Jupiter comes down to that stopping question. Pioneer crossed the asteroid belt and kept going. Voyager used Jupiter as a gravity slingshot and kept going. New Horizons did the same. None of them stopped. Galileo stopped. Juno stopped. And stopping is where the years pile up. Because physics doesn't give you that deceleration for free. You have to earn it with fuel, and fuel means mass, and mass means either a heavier spacecraft or a longer, more looping route to build up enough speed through gravity assists to compensate. New Horizons carried none of that weight. It arrived at Jupiter lighter than most spacecraft in the outer solar system, moving faster than any of them had moved at that point in their journeys, and it blew through the Jovian system like something that had somewhere more important to be, which it did. When mission controllers confirmed the Jupiter flyby had gone as planned, the celebration was real but quick. The Pluto encounter was still 8 years away. New Horizons had covered 365 million miles in 13 months, which sounds extraordinary. And it is, but it was also just the beginning of its actual mission. Jupiter was a milestone, not a finish line. The spacecraft that broke the record for reaching Jupiter treated Jupiter as a pit stop, and that inversion tells you almost everything you need to understand about what speed costs and what it requires. What it requires is commitment to not stopping, not slowing, not capturing into orbit, not deploying a probe, not circling for months while your instruments gather data in detail. You pick up speed, you use the gravity of the largest planet in the solar system to go even faster, and you keep moving until your actual destination comes into view years later. That's the bargain. That's what 13 months to Jupiter actually looks like. Were you watching and wondering whether New Horizons could have stayed? Technically, a spacecraft could be designed to move fast and still slow down, but the fuel required to brake from 52,000 miles per hour into Jovian orbit would have made the spacecraft so heavy that it never could have reached that speed in the first place. The record and the mission are inseparable. You cannot have the speed without the commitment to keep it. 13 months is the fastest any human-made object has ever traveled from Earth to Jupiter, and the condition attached to that record is the same condition that makes it almost irrelevant for any mission that actually needs to be there. New Horizons never stopped. The gravity assist is the closest thing to a free lunch that orbital mechanics allows, and understanding it changes how you think about every number you'll ever hear about spacecraft travel times. Here is what is actually happening. A spacecraft coasting through the solar system carries a fixed amount of energy. If you want it to go faster, you need to add energy somehow, and rockets burn fuel to do that. But there is another way. If you can get close enough to a planet that is already moving through space at high speed, the planet's gravity will grab you and pull you through a curved arc. And if the geometry is right, you come out the other side going faster than you went in. The planet's momentum bleeds over into yours, not through any physical contact, just gravity acting on both objects, doing the math the planet barely notices. Jupiter, for example, has a mass of roughly 318 Earths. A spacecraft weighing a few tons is stealing a sliver of momentum from something so massive the effect is unmeasurable. But to the spacecraft, that stolen speed can mean thousands of miles per hour added without burning a single gram of propellant. You entered the encounter going one speed. You left going a different one. The orbit of the planet is functionally unchanged. Yours is not. The geometry is everything, and this is where most people's intuition breaks down. You cannot just fly close to a planet and expect to gain speed. The direction of approach determines whether you accelerate or slow down. If you approach a planet roughly from behind, swinging in on the trailing side in the direction of the planet's orbital travel around the Sun, you gain speed. The planet's gravity acts like a sling, pulling you forward through its arc and releasing you at higher velocity. Come in from the wrong angle, from ahead of the planet in its orbital path, and the effect runs in reverse. You lose speed. The planet bleeds off your momentum instead of lending you some. Getting this right requires calculating not just where the planet is, but where it is going, how fast it is traveling, and exactly what angle puts your trajectory on the correct side of it. Think of a ball thrown against the side of a moving train. If you throw it toward the side of the train that is coming at you, the ball bounces back faster than you threw it. The train's motion transfers into the ball. Throw it against the side moving away, and the opposite happens. The spacecraft is the ball. The planet is the train. The trick is choosing your angle. Nobody sat down and derived this from pure theory and then built a mission around it. The practical realization came gradually. Early mission planners focused almost entirely on direct trajectories, how much fuel to burn, what angle to launch, how long to coast. But as orbital mechanics computing improved in the 1960s, engineers started looking at planetary encounters differently. Michael Minovich, a UCLA graduate student, worked through the mathematics of gravity assists in the early 1960s and demonstrated that flybys weren't just hazards to avoid or brief data collection opportunities. They were velocity sources. Gary Flandreau, working at JPL in 1965, took that further and identified the planetary alignment in the late 1970s that would allow a spacecraft to hop from Jupiter to Saturn to Uranus to Neptune on a single continuous chain of gravity assists. That insight became the Voyager missions. Once the concept was established, mission designers started using it aggressively. The question became how many flybys you could chain together, and what combination of planets would give you the most useful velocity change for the least detour time. The Galileo mission is the extreme case. Galileo was the first spacecraft designed to orbit Jupiter, launched in 1989. The problem was weight. The spacecraft was heavy, carrying a full orbital science package and a descent probe intended to dive into Jupiter's atmosphere. The rocket that launched it, the space shuttle plus an upper stage, simply did not have the energy to send something that massive on a direct path to Jupiter. A direct trajectory was not available with the hardware on hand. So mission planners designed something unusual. Galileo flew to Venus first. That flyby added velocity. Then it swung back to Earth for a second boost. Then it swung out toward the asteroid belt, turned around, and came back to Earth again for a third flyby. 2 Earth flybys, 1 Venus flyby, and each one added speed, bending Galileo's orbit outward toward Jupiter a little more each time. The total path covered roughly 2.4 billion miles to reach a planet that is, at closest approach, about 365 million miles from Earth. The spacecraft looped through the inner solar system twice before it had enough energy to make the outer solar system crossing. It took just over 6 years. That is not a failure of mission design. That is mission design working exactly as intended, solving an otherwise impossible energy problem with what was actually available. The detours were the mission. Without the gravity assists from Venus and Earth, Galileo simply could not have reached Jupiter at all on that hardware. The choice was not between a direct fast trip and a slow looping one. The choice was between the looping path and no mission. Why can't every mission just do what Galileo did? Because the planets have to be there. A gravity assist requires a planet to be in the right position at the right time when the spacecraft arrives. You cannot schedule a Venus flyby if Venus is on the wrong side of the Sun during your transit window. The geometry has to work. And that geometry is determined by orbital periods that operate on timescales of years, completely indifferent to launch schedules or budget approvals. The Grand Tour alignment that made the Voyager missions possible, that rare configuration of Jupiter, Saturn, Uranus, and Neptune lined up for sequential flybys, occurs roughly once every 175 years. Miss it, and you wait 175 years. The Galileo route worked in 1989 because Venus and Earth were positioned usefully in those years. Run the same mission in a different decade, and the geometry might not cooperate as well. Every gravity assist sequence is a negotiation with the solar system's calendar. There is also a time cost. Each flyby adds distance to the route. Each additional loop through the inner solar system adds months or years to the journey. The velocity gain has to be weighed against the time lost making the detour. For Galileo, the math said the 6 years was acceptable. For a mission that needed to arrive quickly, a long gravity assist chain would be counterproductive. New Horizons used Jupiter for a gravity assist on the way to Pluto. One flyby, one boost, no long detours, 13 months to Jupiter. That was the right trade for that mission. Galileo's route was the right trade for its mission. Every mission to Jupiter has used some form of gravity assist, and the debate between mission designers is never whether to use them, but how many detours are worth taking before the time savings become time losses. Juno launched in August of 2011, reached Jupiter in July of 2016, and when it arrived it was moving so fast that entering orbit required one of the most precisely timed engine burns in the history of spaceflight. 5 years of travel, and the hard part hadn't even started yet. The thing people miss about Juno is what the arrival actually looked like. The spacecraft had been falling toward Jupiter for months, pulled steadily inward by the planet's gravity well. By the time it reached closest approach, it was moving at roughly 130,000 miles per hour relative to Earth. No spacecraft had ever entered orbit around another planet at that kind of speed. That record didn't belong to a spacecraft designed for speed. It belonged to a spacecraft that had simply been falling toward the most massive planet in the solar system for 5 years and couldn't avoid going fast. To enter orbit rather than shoot straight past Jupiter, Juno had to fire its main engine for exactly 35 minutes. Not 30, not 40. 35 minutes of continuous burn to bleed off enough velocity to be captured by Jupiter's gravity. If the engine cut out early, Juno would have sailed past the planet and kept going into deep space, mission over. If it burned too long, the spacecraft would have fallen too deep into Jupiter's gravity, which brings its own set of catastrophic problems. The margin between those two outcomes was the width of a very precise calculation made by engineers sitting in Pasadena, California, 48 minutes of light speed away. By the time the signal confirming the burn had started arrived at mission control, the burn was already finished. Whatever happened during those 35 minutes happened without any possibility of human intervention. The spacecraft made it. But it was not a situation that invited much relaxation. Now here's the part worth holding in your mind. Jupiter's radiation environment is not a minor hazard. It is one of the most intense radiation fields anywhere in the solar system. Jupiter's magnetic field is roughly 20,000 times stronger than Earth's, and it does what strong magnetic fields do. It traps charged particles and whips them up to extreme energies. The radiation belts around Jupiter make Earth's Van Allen belts look gentle by comparison. Close to the planet, radiation levels are enough to destroy unshielded electronics within hours, not months. Hours. Engineers designing Juno knew this going in, and they built a solution that weighs about 400 pounds and is made of titanium. The radiation vault, a box, essentially, housing the spacecraft's most critical electronics, shielded against the worst of what Jupiter can throw. It works, but it doesn't work forever. Jupiter's radiation has been slowly degrading Juno since the moment it entered orbit. Every pass through the inner radiation belts takes a small toll on the hardware. The spacecraft was not designed to last indefinitely in that environment. The question was always how long it could hold together. What has Juno actually found? Quite a bit, it turns out. Before Juno, nobody had imaged Jupiter's poles in detail. The Voyager flybys and Galileo's orbital geometry both kept those regions mostly out of view. Juno's polar orbit was specifically chosen to change that. What the cameras captured looked almost nothing like the banded, orderly Jupiter most people picture. The poles are covered in enormous cyclones, densely packed, some of them thousands of miles across, churning in patterns that don't match anything in existing models. The South Pole has a central cyclone ringed by 5 more. The North Pole has a central cyclone ringed by 8. Why those specific numbers? Nobody has a clean answer yet. Beyond the poles, Juno measured Jupiter's magnetic field with a precision that hadn't been possible from a distance. The field turned out to be stronger than expected and stranger in its distribution, lopsided, concentrated in ways that suggest the planet's interior is more complicated than the relatively simple layered models that had been standard. Juno's gravity measurements have added to that picture, hinting at a fuzzy, diffuse core rather than the compact rocky center many models assumed. Jupiter, it turns out, is not nearly as well understood as its centuries of observation might suggest. Getting a spacecraft into orbit around it was what it took to find that out. Juno's original mission was supposed to end in February of 2018. The radiation accumulation had been expected to degrade the spacecraft to a point where science return would drop below acceptable levels. That deadline came and went, and Juno was still functioning. NASA extended the mission, then extended it again. As of now, the spacecraft is still in operation. Its mission scope expanded to include close flybys of several of Jupiter's moons: Ganymede, Europa, Io. Each one is a target that future missions will study in much more detail. Juno is, in some ways, doing advanced reconnaissance for whatever comes next. The story of Juno is really the story of what it costs to actually stop at Jupiter. New Horizons got to Jupiter faster. Pioneer got there first. Voyager found the most dramatic things. But Juno is the one that stayed, and staying required a 5-year journey, a 35-minute engine burn with no margin for error, and a spacecraft armored against one of the most hostile environments any human-built object has ever entered. Juno is still operational as of this writing, slowly being degraded by radiation that is unlike anything spacecraft experience anywhere else in the solar system, still returning data from a world that keeps revealing things nobody predicted. The Parker Solar Probe has reached speeds of 430,000 miles per hour relative to the Sun, which makes it the fastest object humanity has ever built. And if you could apply that speed to a journey to Jupiter, the trip would take about 43 hours. That number deserves a second to land. 43 hours. Not years, not months. Less than 2 days to cross hundreds of millions of miles. So why aren't we doing that? Why is every mission we've talked about measured in years when the fastest thing we've ever built could theoretically make the trip before the week is out? Here's the part that most people miss. Parker's speed is not the kind of speed you can aim at something. That 430,000 miles per hour is orbital velocity, the speed the spacecraft reaches when it falls toward the Sun on an extremely elongated orbit, swinging close enough that the Sun's gravity is pulling it like a stone in a slingshot. At the bottom of that swing, near perihelion, Parker is moving faster than anything we've ever built. But that speed is pointed sideways, tangent to the orbit, not outward toward Jupiter. It's the same reason a racing car going around a banked curve isn't traveling in the direction it needs to go next. Speed and direction are not the same thing. The distinction between orbital speed and transfer speed is one of those things that sounds technical until you picture it clearly. Parker isn't rocketing away from the Sun at 430,000 miles per hour. It's orbiting the Sun at that speed, sweeping around it in an arc. Every time it reaches perihelion, it's screaming through the inner solar system in a curved path. To actually redirect that speed outward toward Jupiter, you'd have to fight the orbital geometry entirely. The Sun's gravity is what gave Parker that speed, and the Sun's gravity is also what makes it nearly impossible to use that speed to escape into the outer solar system. You'd have to burn enormous amounts of fuel just to change the direction of the momentum, which would cost more energy than the speed gain was worth. Run the thought experiment anyway, though, because it's worth running. Jupiter's average distance from Earth is roughly 444 million miles. If a spacecraft could maintain 430,000 miles per hour in a straight line, not an orbit, just a straight burn, it would cover that distance in just over 43 hours. That's a Wednesday to a Friday. You launch, you watch a couple of movies, you do some reading, and then Jupiter is filling the window. The physics of that trip aren't violated by any law of nature. Nothing in the universe says you cannot move a spacecraft at that speed through that distance. Light takes about 43 minutes to reach Jupiter from Earth, and light is the fastest thing permitted by physics. A spacecraft at Parker's peak speed would be about 60 times slower than light. That is, in cosmic terms, still staggeringly fast. What stops us is energy. The amount of energy required to accelerate a meaningful payload to 430,000 miles per hour and sustain it there is not slightly beyond current technology. It is orders of magnitude beyond it. To understand what that means in concrete terms, think about what it costs to get something off the ground. A heavy lift rocket like the Falcon Heavy burns through roughly 500 tons of propellant to lift maybe 60 tons of spacecraft into low orbit. And that's just getting to orbit, moving at about 17,500 miles per hour. To get to 430,000 miles per hour, you'd need to accelerate the spacecraft to roughly 25 times that velocity. The fuel required using conventional chemical propulsion would be so massive that no rocket we've ever built or are planning to build comes anywhere close to carrying it. The rocket equation turns against you fast. Every pound of fuel you add to go faster requires more fuel to accelerate that fuel, which requires more fuel on top of that, in a compounding spiral that collapses under its own weight before you get anywhere near Parker's speed with a useful payload. New Horizons, the fastest spacecraft we ever launched away from Earth, left at about 36,400 miles per hour. That's fast. But 430,000 miles per hour is almost 12 times faster. The energy difference between those two speeds isn't 12 times. Kinetic energy scales with the square of velocity, which means the energy required grows much faster than the speed itself. The gap is not a linear climb, it's a wall. None of this means the idea is dead. It means we haven't built the engine that can get us there yet. Parker Solar Probe didn't reach those speeds with chemical propulsion. It fell. The question is whether we'll eventually develop propulsion that can generate that kind of velocity without needing the sun's gravity to do the work for us. The speed is physically possible. The problem is energy, and the gap between what current propulsion can deliver and what that calculation requires is not a small gap. Jupiter's position relative to Earth changes constantly, and every 13 months or so, the geometry lines up in a way that makes the journey reasonably efficient. Miss that window, and the options for getting to Jupiter without a catastrophic fuel penalty become considerably worse. This is what engineers call the synodic period. It's the time it takes for Earth and Jupiter to return to roughly the same relative positions after one cycle. Earth laps Jupiter about once every 398 days. That's your window. Not every 365 days, not every year on the calendar, every 398. And the window itself isn't a wide open door. It's narrow. A few weeks on either side of the optimal date, and the geometry starts sliding away from you fast. Here's what that actually means. When Earth and Jupiter are positioned just right, a spacecraft can leave Earth on an efficient trajectory and arrive at Jupiter in a reasonable amount of time without burning through catastrophic quantities of fuel. The math lines up. The orbit works. Slide that launch date by a month in either direction, and the same trajectory now requires noticeably more fuel to compensate. Or you accept a longer coast through the void, or both. Slide it by 2 months, and the mission either becomes more expensive or slower in ways that cascade through the entire mission design. The solar system is not generous with these windows. Mission planners know this better than anyone. In the months before a launch window opens, the trajectory teams are running thousands of calculations. They're modeling every variation. What if the rocket is delayed 3 days? What if it's delayed 10 days? What if a component fails and they lose the primary window entirely? For every scenario, there's a backup. And the backup is almost always worse. It's slower, or more expensive, or it requires a different gravity assist sequence that adds months to the journey. The primary window is primary for a reason. Everything downstream from the launch date is shaped by it. Galileo is the clearest example of this. The spacecraft was delayed multiple times before launch, and each delay forced engineers to rethink the trajectory. Eventually, the mission ended up on a path that used Venus, then Earth again, as gravity assist waypoints, just to accumulate enough speed to reach Jupiter. 6 years. That wasn't the original plan. That was the consequence of working around constraints that kept shifting the geometry. The solar system doesn't hold the window open while the paperwork clears. Now put a human crew on board, and the problem multiplies. A robotic spacecraft sitting on the pad, waiting out a delay, is inconvenient. A crewed spacecraft sitting in low Earth orbit waiting for the window to come back around is a different category of problem. Every extra week in orbit before departure is a week of food consumed, oxygen used, water recycled through systems that wear out. It's a week of radiation exposure outside Earth's protective magnetic field. The crew hasn't gone anywhere yet, and the mission is already accumulating cost in the most direct biological sense. There's no pause button. You can't freeze the consumables, and you can't freeze the crew. The clock runs whether you're moving toward Jupiter or waiting for the chance to leave. This is one reason why human Jupiter missions scare mission architects in ways that human Mars missions don't, at least not to the same degree. Mars windows are also constrained. They open roughly every 26 months, but the journey is shorter. Miss a Mars window and the extra weight hurts. Miss a Jupiter window and you're looking at another 13 months before a comparable opportunity returns, and you've spent those 13 months burning through resources without moving an inch toward the destination. The return window compounds everything. Once a spacecraft reaches Jupiter, getting home isn't as simple as pointing back at Earth and firing the engines. Earth has moved. The favorable alignment for a return trajectory is its own separate calculation, and it doesn't necessarily fall whenever the mission team would prefer it to. A crewed mission that arrives at Jupiter might face a wait of several months before the return window opens into something efficient. That's months near Jupiter, inside its radiation environment, before the journey home even starts. The total mission duration isn't just the travel time out and back. It's travel time plus the residency period forced on you by the geometry. This is the piece that most explanations of Jupiter travel time leave out. The journey doesn't end when you arrive. It restarts when the planets allow it. And there's no negotiating with orbital mechanics. Engineers can optimize trajectories, select the best launch dates, build in contingencies, and run every simulation available. What they cannot do is move Jupiter. What they cannot do is accelerate Earth around its orbit to create a more favorable angle. The window is where it is because the planets are where they are, and that reality sits upstream of every schedule, every budget approval, every technical delay, every mission review that has ever been held about sending anything to Jupiter. The solar system runs on its own schedule, and the most carefully planned mission in history cannot open a favorable launch window a single day before the orbital geometry allows it. When Juno's main engine fired for the 35-minute burn that put it into orbit around Jupiter, the signal confirming that the burn had started arrived at Mission Control in California 48 minutes after the engine lit, by which point the burn was already finished. The team in Pasadena could only wait. They had loaded the commands, run the simulations, checked the software, and then let go. What happened at Jupiter stayed at Jupiter for nearly an hour before Earth found out. This is the 45-minute problem. Radio signals travel at the speed of light, and nothing in the known universe moves faster. At Jupiter's closest approach to Earth, a signal takes about 33 minutes one way. At the farthest point, 53 minutes. The average works out to roughly 43 minutes. So a round-trip conversation, you send a message, you wait for a reply, takes somewhere around 86 minutes under typical conditions. An hour and a half. Not because of equipment limits or antenna strength, because of distance and because light is the speed limit. Think about what that means for a spacecraft executing a critical burn. Juno's orbital insertion was the single most dangerous moment of a 5-year mission. Fire too little, and Juno shoots past Jupiter and disappears into the outer solar system. Fire too much, and the spacecraft plunges too deep. The margin was narrow, and the people who built it, who designed every circuit and wrote every line of code, were sitting in a room on Earth watching a screen, completely unable to help. By the time any signal telling them something had gone wrong could have reached them, the outcome would already be decided. That changes everything about how you build a spacecraft. The computers aboard Juno had to be capable of making decisions without anyone's permission. If a sensor reads an anomaly mid-burn, the spacecraft handles it. It has to. There is no other option. Engineers spend years writing fault protection software, branching logic that anticipates failures and tells the spacecraft what to do when things go sideways and Earth is 43 minutes away and silent. You are not flying the spacecraft from the ground. You are writing instructions for a machine that will fly itself in a situation nobody can fully predict, around a planet that takes nearly an hour to talk to. Here's a scenario worth sitting with. Something goes wrong during a critical maneuver. Maybe a thruster misfires. Maybe a sensor gives a bad reading. The spacecraft sends an alert immediately. That signal leaves Jupiter at the speed of light and travels for 43 minutes across the solar system before it reaches Earth. Mission controllers read the alert. They assess the situation. They write a response command and send it back. That return signal takes another 43 minutes. By the time any human instruction reaches the spacecraft, 86 minutes have passed. In those 86 minutes, the spacecraft has been completely on its own, deciding what to do based on whatever fault protection logic it was given before the mission started. If the logic was good, the mission survives. If it wasn't, there is nothing anyone on Earth can do about it. Galileo, Juno, New Horizons at closest approach. Every critical event in the Jovian system has unfolded this way, autonomously. The spacecraft running through its instructions, the ground team watching a signal delay that makes real intervention physically impossible. There's something almost haunting about it. Hundreds of engineers who gave years to building a machine, and when the most important moment arrives, all they can do is wait and see what the machine decided. Now put humans in that spacecraft. The communication delay doesn't change. It's still 43 minutes each way, still 86 minutes round trip. An astronaut on a Jupiter mission who runs into a medical emergency cannot call Earth and get real-time guidance the way someone in low Earth orbit can. Mission control cannot watch a problem develop and talk the crew through a fix. By the time Earth hears about an emergency, the crew has already been managing it for the better part of an hour. Whatever training they have, whatever equipment is aboard, whatever decisions need to be made, those are made by people who are genuinely, completely alone. Not in the romantic sense, in the operational sense. The communication structure that holds every human spaceflight together right now, the constant contact with ground teams, the real-time troubleshooting, the flight director's monitor, ring every system. None of that works at Jupiter. The crew becomes its own mission control, its own medical team, its own engineering support. Every spacecraft at Jupiter operates alone, responding to a universe that is moving faster than the speed of human conversation, and for a human crew that gap between event and response would be one of the most disorienting aspects of the entire journey. Jupiter's magnetic field is roughly 20,000 times stronger than Earth's, and that fact alone reshapes every calculation about what it would actually take to operate there. Most people hear that number and file it away as an interesting detail. It is not a detail. It is the dominant physical reality of the entire Jovian system, and it affects everything from how a spacecraft is built to whether a human being could survive anywhere near that planet. The field extends outward from Jupiter for tens of millions of miles in every direction. If you could see it with your eyes, it would be the largest structure in the solar system, bigger than the Sun itself. And inside that field, something dangerous is always happening. Here is what a magnetic field does to charged particles moving through space. It traps them. It bends their paths. It forces them into tight spiraling loops. And every time a particle spirals, it picks up energy. Electrons and protons caught inside Jupiter's field get accelerated to velocities that would be considered extreme, even in a particle accelerator on Earth. They do not just drift around passively, they move at a significant fraction of the speed of light, and they do not hit you like a wave. They hit you like a continuous storm of invisible bullets, passing straight through metal, straight through circuitry, straight through biological tissue. The radiation belts around Earth, the Van Allen belts, are genuinely hazardous. Satellites avoid them when possible. Astronauts on the International Space Station stay below them. Jupiter's equivalent is roughly 1,000 times more intense at close range. 1,000 times. What does that actually mean for a spacecraft? Unshielded electronics near Jupiter would not degrade slowly over months. They would start failing within hours. The sensors, the computers, the memory systems, all of it would accumulate damage faster than the hardware could compensate. Early mission designers understood this. Every spacecraft sent to Jupiter has had to reckon with it in some form. The Pioneer probes were simple enough that radiation damage was manageable. Voyager flew through the system quickly, minimizing exposure time. But Galileo, which orbited Jupiter for nearly 8 years, had no such luxury. It was inside that radiation environment continuously, and the damage accumulated. Instruments degraded. Tape recorders malfunctioned. By the time engineers deliberately crashed Galileo into Jupiter's atmosphere in 2003, the spacecraft was a shadow of what it had been when it arrived. 8 years of Jupiter radiation did that. Juno took a different approach. Its designers knew they could not stop radiation from reaching the spacecraft entirely, so they built a vault. An actual titanium box, roughly the size of a large carry-on bag, housing the most sensitive electronics aboard. Titanium is dense. Dense materials absorb radiation better than light ones. That vault reduced the radiation dose to Juno's core computers by a factor of roughly 800. That is the kind of engineering that does not make headlines, but makes the entire mission possible. And it still was not enough to protect Juno indefinitely. The spacecraft was originally planned for a shorter mission. It has been extended repeatedly because it keeps functioning, but Jupiter's radiation is still slowly working through the shielding. Every orbit takes a toll. Juno also uses a polar orbit specifically designed to limit time in the worst radiation zones. Jupiter's radiation belts are concentrated around the equatorial plane of the planet, much like Earth's Van Allen belts, but vastly more intense. By flying in long, looping orbits over the poles rather than circling the equator, Juno spends most of its time in regions where the radiation is less concentrated, dipping down toward the planet only briefly during each close pass. The orbit is not shaped by scientific preference, it is shaped by survival. That is what radiation does to mission design at Jupiter. It does not just influence the plan, it dictates the geometry. Now think about what this means for a human crew. The numbers stop being engineering problems and start being medical ones. A dose of radiation is measured in sieverts. A chest X-ray delivers roughly 0.1 millisieverts. An astronaut on a 6-month International Space Station mission receives around 80 millisieverts from cosmic background radiation in low Earth orbit. NASA's career limit for astronauts, the maximum total dose considered acceptable over a lifetime, sits around 600 to 1,000 millisieverts, depending on the individual. In close Jupiter orbit, unshielded, a human being would receive a lethal dose in a matter of hours. Even inside a heavily shielded spacecraft, estimates for radiation exposure near Jupiter run into thousands of millisieverts per day in the inner radiation belts. There is no shielding solution that makes extended close operations survivable, not with any material we currently build spacecraft from. This is why any serious discussion of human missions to the Jovian system does not involve humans orbiting Jupiter closely at all. The practical scenarios place the crew much farther out. Callisto, the outermost of the 4 large Galilean moons, sits beyond the worst of Jupiter's radiation belts. Operations based from Callisto would receive radiation doses that are dangerous but far more manageable than close Jovian orbit, somewhere in the range of what a Mars mission would experience from deep space cosmic radiation during the transit. Europa, which has the most compelling scientific case for exploration, sits deep inside the radiation environment. A crewed landing on Europa would be extraordinarily hazardous. The radiation dose on Europa's surface is estimated at around 540 millisieverts per day. A crew could not stay long. Were they to spend even a week there, they would have absorbed a significant fraction of a lifetime's acceptable dose in a single visit. Something else worth holding in your mind. The journey to Jupiter takes years. During those years, the crew is outside Earth's protective magnetosphere, exposed to cosmic radiation streaming in from every direction. That background dose accumulates the entire way out and the entire way back. By the time a crew arrived at Jupiter, they would have already spent years collecting radiation before the Jovian environment added its own contribution on top. The two problems do not exist in isolation. They stack. A mission that begins with several years of deep space transit, radiation ends with an arrival at one of the most hostile radiation environments in the solar system. The exposure is not sequential in the sense of being separate challenges with a gap between them. It is continuous, from the moment the spacecraft leaves Earth orbit to the moment it returns. This is what makes Jupiter different from Mars in ways that go beyond simple distance. Mars is deep space. Mars is far. But Mars sits outside Earth's magnetosphere without adding a planetary radiation belt of its own. Jupiter brings both problems simultaneously. The multi-year journey gives the crew a radiation burden before they even get there, and then the destination itself demands that they never get too close to what they came to study. Every instrument aboard has to be rated for an environment that destroys unshielded hardware in hours. Every orbit has to be designed around what the radiation belts will allow, not just what the science team wants. The radiation is not a detail in the margin of a Jupiter mission. It is a central constraint that shapes the spacecraft design, the orbital profile, and the question of whether any human crew could ever safely approach the planet at all. Every number about getting to Jupiter changes the moment you put humans on the spacecraft, not by a small amount. Everything covered so far, the trajectories, the gravity assists, the orbital insertion burns, the radiation vaults, all of that was built around machines. Machines that don't need to eat, machines that don't need air, machines that can be powered down to almost nothing for months at a stretch while they coast through the dark between planets, waiting for arrival day. A spacecraft's computer doesn't notice the emptiness. It doesn't lose muscle mass. It doesn't develop blood clots or depression or a craving for something other than recycled water. The moment you put a human crew on that spacecraft, every assumption underneath every number changes simultaneously. The changes stack on top of each other in ways that compound fast. Start with the basics. A human crew needs roughly 1.8 kilograms of food per person per day. They need water. Some can be recycled, but recycling systems are heavy and imperfect. They need oxygen generation, carbon dioxide scrubbing, temperature control, pressure maintenance, medical supplies for conditions you can't predict years in advance. They need exercise equipment because microgravity begins stripping bone density at roughly 1 to 2% per month. Without aggressive countermeasures, a crew arriving at Jupiter after years in transit would be in no condition to do useful work. They need lighting calibrated to support circadian rhythms. This was because without proper light cycles, sleep degrades and judgment degrades with it. They need psychological support structures, real ones, not gestures toward the idea of them, because 6 years in a confined space with the same small group of people, with no possibility of emergency return and a 45-minute communication delay to Earth, produces the kind of stress that no standard astronaut selection process, WAL, is designed to evaluate. None of this is theoretical. We already know what happens to human bodies on long missions. Astronauts returning from 6 months on the International Space Station routinely struggle to walk under their own weight. Their cardiovascular systems have partly forgotten what gravity requires of them. Their eyes have changed shape from fluid redistribution toward the head during months of weightlessness. Their immune systems behave differently. 6 months produces effects serious enough that returning astronauts spend weeks in rehabilitation before they're considered recovered. A Jupiter mission, even under the most optimistic trajectory assumptions, would last somewhere between 6 and 9 years round trip. That is not 6 months times 12. The body doesn't scale that way. Nobody has data on what 6 years of continuous microgravity does to a human being. This was because nobody has ever done it. The data we do have from shorter missions is not encouraging. Then there is the radiation. This deserves to be said plainly. Beyond Earth's magnetic field, space is not empty in the benign sense the word implies. It is filled with high-energy particles, galactic cosmic rays streaming in from outside the solar system. Solar energetic particles that arrive without warning when the sun has an active day. Earth's magnetosphere deflects most of this. Once a spacecraft leaves that protection, the crew is exposed to all of it, continuously, for the entire journey. A multi-year trip to Jupiter and back would expose each crew member to radiation doses that, by current estimates, significantly exceed what NASA considers an acceptable career limit for astronauts. We are not talking about a modest increase in risk. We are talking about doses that substantially elevate lifetime cancer probability and may cause measurable cognitive degradation, memory, processing speed, the kinds of functions that a crew member would need to perform complex tasks years into the mission. There is no complete engineering solution to this right now. You can add shielding, but shielding is heavy. Heavy means more fuel, and more fuel means more mass, and more mass means more fuel still. At some point, the shielding itself becomes part of the problem it was meant to solve. Which brings us to the mass problem, because it sits underneath everything else like a foundation. Every system you add to keep the crew alive and functional adds kilograms. Food for 6 people for 6 years. Water recycling hardware robust enough to last without replacement parts. Medical equipment comprehensive enough to handle a serious illness or injury with no hospital within 400 million miles. Exercise machines that can sustain a workout load intense enough to slow bone loss across years of use. Radiation shielding sufficient to reduce, not eliminate, reduce, the exposure to something closer to acceptable levels. Communication equipment capable of maintaining contact across the distances involved. spare parts for all of the above. This was because nothing in the history of human spaceflight has ever operated for 6 consecutive years without something breaking. Add all of that up, and you have a spacecraft that is not comparable to Juno or New Horizons or Galileo in any meaningful sense. You have something that has to be built and launched at a scale no rocket ever constructed has come close to achieving. The Juno spacecraft weighed about 3,600 kilograms at launch, most of which was fuel. A crewed Jupiter vehicle, carrying everything that crew survival requires, would likely need to be an order of magnitude heavier, and that estimate assumes recycling systems that work at efficiencies we haven't demonstrated over multi-year durations. Propulsion technology more capable than what currently exists. The Saturn V, the most powerful rocket humanity has ever successfully flown, could lift about 130,000 kilograms to low Earth orbit. That sounds like a lot. For a crewed Jupiter mission, it is a starting point for a conversation about how many launches it would take to assemble the actual vehicle in orbit before the journey could begin. This is why no space agency has a funded, active program for sending humans to Jupiter. It is not a failure of imagination. The vision is there. The physics is understood well enough to know what the requirements are. The gap is between the requirements and what any existing or near-term technology can meet. That gap is not a narrow one you could close with a focused decade of development. It is wide enough that serious mission architects who study it professionally tend to frame a crewed Jupiter mission as a late 21st century possibility at the earliest, contingent on propulsion advances, life support advances, radiation mitigation advances, a level of sustained political and financial commitment that no space program anywhere has maintained for that length of time. No space agency currently has an active, funded program for sending humans to Jupiter, and the math of why that is makes the gap between ambition and reality feel almost geological in scale. The longest continuous spaceflight in history was 437 days, set by Russian cosmonaut Valery Polyakov aboard the Mir space station in 1994 and 1995, and when he landed, he was carried off the spacecraft because his legs couldn't support his weight. That is 437 days. One person, one station orbiting just a few hundred miles above Earth, still inside the protective bubble of Earth's magnetic field, still close enough that a rescue mission was physically possible. Polyakov's record is extraordinary. It is also, relative to a Jupiter mission, a warm-up lap. A crew heading to Jupiter and back under the best currently imaginable scenario would spend somewhere between 6 and 9 years in transit. Do the math on what Polyakov's experience represents in that context. His 437 days is less than a fifth of the low end of that range, and he came home unable to walk. Here is what happens to the human body in microgravity, and it starts almost immediately. Bone density drops at roughly 1 to 2% per month. That sounds modest until you realize that over 6 years, the accumulated loss is staggering. The equivalent of what someone might experience over multiple decades of normal aging on Earth, compressed into a single mission. The skeleton is a dynamic structure. It responds to load. Take away gravity, and the body reads that absence as a signal to stop maintaining bone mass it no longer needs. The result is something close to accelerated osteoporosis, and no current countermeasure fully stops it. Muscle atrophy follows the same logic. Without gravity to push against constantly, the muscles that hold the body upright, move it through a room, keep it functional under the weight of its own frame, those muscles shrink. ISS astronauts exercise 2 hours a day specifically to slow this process down. They return from 6-month missions and still struggle to stand. Their bodies have to relearn what gravity feels like. Stretch that mission to 9 years, and you are asking the body to maintain function in a regime it was never designed for a duration that has no precedent in the history of human spaceflight. Then there is the fluid shift. In microgravity, bodily fluids redistribute upward, pooling toward the head. This creates pressure changes inside the skull that affect the eyes. A significant fraction of long-duration ISS astronauts have returned with measurable changes to the structure of their optic nerves and the shape of their eyeballs. Some experienced lasting vision problems. The condition has a name now: spaceflight-associated neuroocular syndrome, and researchers are still working out exactly what causes it and how to prevent it. A crew traveling to Jupiter for several years would be living inside that problem for the entire journey. The cardiovascular system deconditions too. The heart, like any muscle, adapts to the demands placed on it. In microgravity, those demands change dramatically. The result over time is a heart that is smaller, less efficient under gravity, and less capable of handling the sudden return to a 1G environment. The immune system shifts in ways that are not fully understood. Latent viruses that the body normally suppresses can reactivate. The combination of radiation exposure, disrupted sleep cycles, stress, and altered immune function creates a health environment that has no clean analog in any terrestrial setting. None of this even touches the psychological dimension yet. 6 years in a spacecraft the size of a large apartment, with the same small group of people, no possibility of leaving, no possibility of emergency return once you're past a certain point in the trajectory. Earth, over the first few months of the journey, shrinks from a visible disk to a bright star to something indistinguishable from the background. Then it disappears entirely into the glare. Communications have a 45-minute one-way delay. If something goes wrong, with the crew, with a relationship, with someone's mental health, there is no therapist to call. There is no home. There is a message that takes 90 minutes round trip to deliver a reply. What behavioral research exists on long-duration isolation is not especially reassuring. Antarctic winter-over cruise, small teams isolated for months in extreme conditions, show measurable cognitive changes, elevated tension, communication breakdowns, and what researchers have called third-quarter phenomenon, a significant dip in morale and function that occurs roughly 3/4 of the way through a long isolated deployment. These are people who can see the sky. Submarine crews operate in confined isolation for months at a time, and their psychological management protocols are extensive, carefully studied, and still produce casualties. Those missions are measured in months. A Jupiter mission is measured in years. The honest thing to say about all of this is that some of these problems are engineering problems. Better exercise equipment, smarter radiation shielding, improved nutrition. These are things that can be built and refined, but some of them are not engineering problems. Bone loss in microgravity, at its core, is biology responding to the absence of a force that shaped the human body over millions of years of evolution. The vision changes are structural. The psychological effects of years of confinement with no exit option are not a software problem waiting for a patch. They are what happens to people in certain conditions, and the conditions of a Jupiter mission are conditions no human has ever actually endured. A Jupiter mission would ask a crew to endure something that makes Polyakov's record look like a warm-up, in an environment where the sun has shrunk to a very bright star and Earth takes 45 minutes to answer your messages. Every serious discussion about human missions to Jupiter eventually arrives at the same problem. The journey is too long with current propulsion technology, and changing that requires either accepting a different kind of mission or developing engines that do not yet exist. So what does exist? What is actually being built, tested, or seriously studied that could change the numbers? Because there are answers, not science fiction answers, real ones. And they range from technologies almost ready to fly to ideas that are genuinely decades away from anything you could put on a launch pad. Each one deserves an honest look, because the difference between where these programs are today and where they would need to be is not a small gap. Start with nuclear thermal propulsion, because this is the most mature option and the most likely to actually fly within most people's lifetimes. The basic idea is not complicated. Instead of burning chemical fuel to generate hot exhaust and thrust, you run propellant through a nuclear reactor. The reactor heats the propellant to temperatures no chemical combustion can match, and it exits the nozzle much faster. Faster exhaust means better efficiency. The technical measure is specific impulse, which is roughly how much thrust you get per unit of fuel. Chemical rockets top out around 450 seconds of specific impulse. A nuclear thermal engine could hit 900 seconds or better. That is roughly double the efficiency. Double the efficiency means either you need half the fuel for the same trip, or you can go considerably faster on the same fuel load. For a Jupiter mission, models suggest nuclear thermal propulsion could cut transit time for an orbital mission down to somewhere between 2 and 3 years. Still not fast, but compared to Galileo's 6 years, it is a different conversation entirely. And this is not theoretical. NASA and DARPA have a joint program called DRACO, Demonstration Rocket for Agile Cislunar Operations, specifically aimed at testing a nuclear thermal engine in space by the late 2020s. That is a real program, with real funding and real contractors working on the reactor design right now. Whether it stays on schedule is a different question, but the direction of travel is clear. Nuclear thermal propulsion is the most credible near-term path toward faster deep space missions, and it has been on paper since the 1960s, when the original NERVA program ran successful ground tests. The technology works. The question has always been political will and money, not physics. Then there is nuclear pulse propulsion, which is the point where this conversation gets genuinely strange. The idea here is to detonate small nuclear bombs behind the spacecraft and ride the shockwave. Sounds absurd, but the math, done seriously by serious people in the 1950s and 60s under a program called Project Orion, is actually compelling. A spacecraft using pulse propulsion could theoretically reach velocities that would put Jupiter within reach in a matter of months. Not years, months. The specific impulse numbers are extraordinary. Tens of thousands of seconds, not hundreds. Freeman Dyson, one of the most respected physicists of the 20th century, worked on Orion and believed it was the most practical path to rapid interplanetary travel. He was not a crank. But Orion died for reasons that had nothing to do with physics. The Partial Nuclear Test Ban Treaty of 1963 prohibited nuclear detonations in space, which is a reasonable policy concern and also a complete showstopper for a spacecraft that works by detonating nuclear bombs every few seconds. No serious development program for pulse propulsion exists today. It lives in the category of ideas that the physics permits, but everything else currently prevents. Ion propulsion is the opposite end of the spectrum, not extreme, but proven. An ion thruster works by accelerating charged particles electrically and ejecting them at very high exhaust velocities. The efficiency is remarkable. The thrust is not. Ion engines produce roughly the force of a piece of paper resting on your hand. Over weeks and months, that whisper of thrust adds up, and because the efficiency is so high, the spacecraft can keep accelerating long after a chemical rocket would have run dry. The Dawn spacecraft used ion propulsion to orbit both Vesta and Ceres in the asteroid belt, something chemically propelled spacecraft could not have done without prohibitive fuel mass. The Hayabusa missions used ion propulsion to reach and return from asteroids. For robotic science missions, ion propulsion is genuinely transformative. For human missions, it is essentially useless. Nobody is waiting 3 years to slowly accelerate to barely useful speeds while the crew ages inside a tin can. Ion propulsion solves the wrong problem for crewed deep space travel. Solar sails are worth mentioning because the concept is genuinely elegant and the physics is real. Sunlight exerts pressure. It is a tiny pressure, but in space, tiny forces over long periods accumulate into real velocity changes. A large enough reflective sail could use that pressure to accelerate a spacecraft without any propellant at all. The problem for a Jupiter mission is geometry. The intensity of sunlight drops with the square of distance from the Sun. At Earth, solar pressure is already small. At Jupiter, which is about 5 times farther from the Sun, the intensity drops to roughly 4% of what it is here. The sail would need to be enormous to generate meaningful thrust that far out, and by the time you have built a sail large enough to matter at Jupiter's distance, you have a structure so large it becomes its own engineering nightmare. Solar sails are promising for missions in the inner solar system and for very small probes. As a path to Jupiter on any useful timescale, they fall short. Laser sails take the solar sail concept and replace sunlight with a ground-based laser array. This is the idea behind Breakthrough Starshot, which proposed using powerful lasers to accelerate gram-scale probes to a fraction of the speed of light for an interstellar mission. For a Jupiter probe, you would not need anywhere near that scale. A laser sail mission to Jupiter could theoretically work for very small payloads, probes the size of a chip, carrying sensors and little else. The laser array would accelerate the probe to high velocity quickly, and it would reach Jupiter in weeks. The catch is the same one that limits solar sails: scaling up. A gram-scale probe cannot carry meaningful science instruments, cannot orbit, cannot return data over long distances with any bandwidth, and certainly cannot carry a crew. As a concept for interstellar exploration or for ultra-miniaturized scout probes, laser sails are fascinating. As a practical path to crewed Jupiter missions, the gap between the concept and the requirement is vast. Fusion propulsion is where the numbers become almost disorienting. A spacecraft powered by fusion, the same process that powers the Sun, could theoretically reach Jupiter in weeks, not months, weeks. The energy density of fusion fuel makes chemical propulsion look like burning wet wood. Theoretical designs have been drawn up, specific impulse numbers have been calculated, trajectory analyses have been run. The physics is coherent. The engineering is not yet real. Controlled fusion has been decades away from practical application for roughly 60 years, and that timeline has not compressed as quickly as anyone hoped. Recent progress in fusion research is genuine. There have been real milestones at facilities like the National Ignition Facility. But the distance between igniting a fusion reaction in a laboratory and building a fusion engine that can safely power a spacecraft is enormous. Fusion propulsion belongs in the honest category of things that would transform everything about the timeline to Jupiter. And that may genuinely arrive someday, but that no one should count on within any specific planning horizon. What this survey reveals is a spectrum. Nuclear thermal propulsion is close, years away, not decades, if the funding holds. Ion propulsion is already flying, but solves the wrong problem for crews. Pulse propulsion is physically compelling, but politically frozen. Solar and laser sails have niches, but not the one we most need. Fusion propulsion is the prize at the end of the road, but the road is long and the end is not in sight. Each of these technologies is real, each has genuine advocates, and each faces barriers between current laboratory status and a flying spacecraft that are measured not in years, but in decades, which is itself part of the honest answer to how long it would take us to reach Jupiter. Start with what we already know actually happened. New Horizons left Earth in January of 2006 and passed Jupiter 13 months later. That is not a theoretical number. That is a real spacecraft, a real trajectory, a real clock. But New Horizons weighed about 1,000 pounds, carried no braking fuel, and had zero intention of stopping. It used Jupiter the way a billiard ball uses a bumper. Angle in, angle out, keep moving. That is the version of the trip that takes 13 months. Everything else is harder. Could something get there even faster than New Horizons? Probably. If you stripped a probe down to its absolute minimum, sensors, transmitter, power supply, nothing else, and launched it on the most powerful rocket currently available, aimed at a favorable orbital window with an aggressive trajectory, 9 or 10 months to Jupiter starts to look conceivable. The physics allows it. The engineering is painful, but not impossible. The catch is that a spacecraft like that would be small. Tiny, really. Not much bigger than a shoebox. And it would scream straight through the Jovian system like a bullet through a doorway, collecting a few hours of data before disappearing into the outer solar system forever. Now ask what happens when the spacecraft needs to stop. This is where the math turns brutal. To enter orbit around Jupiter, a spacecraft has to shed an enormous amount of velocity. Jupiter's gravity will have accelerated it to somewhere around 130,000 miles per hour by the time it arrives, and the spacecraft has to fire engines hard enough to cancel most of that speed. That requires fuel, a lot of it, and fuel has mass, and mass requires more fuel to accelerate from Earth. The rocket equation compounds against you at every step. A spacecraft designed to break into Jovian orbit needs to carry so much propellant that the entire mission architecture changes. Suddenly, you're not talking about 9 months. You're back to 5 or 6 years, even with more capable propulsion than we currently have. For a human crew, the problem gets worse in every direction at once. Humans need food, water, air, and enough shielding to survive years in deep space radiation. A crewed spacecraft to Jupiter would be massive, orders of magnitude heavier than New Horizons. The most optimistic estimates using current chemical propulsion put a round-trip human mission at 6 to 9 years. Not 6 to 9 months. Years. And that assumes everything goes correctly, which deep space missions famously do not guarantee. Here is where nuclear thermal propulsion becomes genuinely relevant rather than just conceptually interesting. NASA and DARPA are actively developing a nuclear thermal engine under the Draco program, with a test flight targeted for the late 2020s. The basic idea is straightforward. Instead of burning chemical propellants to generate thrust, a nuclear reactor heats hydrogen to extreme temperatures and expels it at roughly twice the exhaust velocity of conventional engines. More exhaust velocity means more efficiency. More efficiency means either a shorter trip or a lighter spacecraft, or both. Applied to a Jupiter mission, nuclear thermal propulsion could realistically cut the transit time for an orbital mission down to somewhere around 2 to 3 years. For a crewed round trip, under optimistic conditions, you might be looking at 3 to 4 years each way if the technology matures to the level mission planners are hoping for. That is still not months. But it is a different problem than the one we have today. The gap between those concept studies and an actual flying spacecraft matters. Draco is a real program with real funding, but it is a test of a small demonstrator engine. Scaling that up to something capable of propelling a crewed Jupiter spacecraft is a separate program that does not yet exist, with a budget that has not been approved, on a timeline that nobody has officially committed to. This is the part that tends to get lost when people talk about what future propulsion could do. The physics is sound. The engineering roadmap is plausible. The funded development program is not there yet. So what is the honest answer? With current technology and a robotic spacecraft, the fastest realistic one-way trip to Jupiter is about 13 months, and only under the specific conditions that made New Horizons possible. Light, fast, not stopping. A robotic orbiter takes 5 to 6 years minimum. A crewed mission with current propulsion would take the better part of a decade round trip. A crewed mission with nuclear thermal propulsion, if the technology reaches the necessary maturity, might come down to 3 or 4 years each way. A crewed mission that could make the trip in months requires propulsion that is still theoretical. Fusion drives, laser propulsion, concepts that live in serious peer-reviewed papers, but not in any funded hardware program. Could we see a star perish as it occurred? Was it something we could reach before our technology caught up to our ambition? The distances involved in space travel have a way of making humanity feel very small and very slow and very early in the story. Getting to Jupiter faster is a problem of energy, not of physics, and the line between those two things is the line between what we currently know how to build and what we can currently only calculate. Nobody would spend years in a spacecraft getting to Jupiter to study Jupiter. The planet itself is a sphere of gas and storms with no surface to stand on and radiation belts that would destroy any unshielded human in hours. So the question of why we would ever go there, given everything we now know about how hard getting there actually is, deserves a real answer. And the real answer is not Jupiter. It never was. The real answer is orbiting about 400,000 miles above it. Jupiter has 95 known moons. Most of them are small, captured rocks spinning in distant orbits, nothing remarkable. But 4 of them, the Galilean moons, spotted by Galileo himself in 1610, are worlds in their own right. and one of them may be the most important place in the solar system, at least from the perspective of a species asking whether it is alone. That moon is Europa. It is roughly the size of our own moon. It is covered in a shell of water ice, and underneath that ice sits a liquid ocean. Not a frozen one, a liquid one, kept warm by the tidal forces Jupiter exerts on the moon's interior as it pulls and flexes the rock like bread dough. That ocean is estimated to contain more liquid water than every ocean, lake, and river on Earth combined. Twice over. Some models put it at 3 times. And liquid water is not the only ingredient that makes astrobiologists go quiet and serious when Europa comes up. The ice shell is fractured. Deep cracks run across the surface where the ice has split and refrozen. And in some of those fractures, there are traces of salts and organic compounds that suggest chemistry happening at the seafloor. Hydrothermal vents, possibly. The kind of environment where, on Earth, life turns up in places nobody expected it. Were we watching chemistry that could produce life? That question drives the Europa Clipper mission, which launched in 2024. But a robotic spacecraft, however sophisticated, can only do so much. Here is the thing a human crew can do that no probe can. When something unexpected turns up in a sample, a human scientist on site can stop, look again, and change the plan. That sounds simple. It is not. The 45-minute communication delay means a robotic mission operates on instructions written hours before any given moment. When Curiosity found something unexpected on Mars, mission scientists had to wait until the next planning cycle to redirect it. For something as delicate and time-sensitive as collecting samples from a fracture zone on Europa's ice shelf, that delay could mean the difference between a discovery and a missed opportunity. A human crew operates in real time. That gap matters enormously. Then there is Ganymede. Larger than the planet Mercury, with its own magnetic field, the only moon in the solar system known to generate one, and its own subsurface ocean beneath an ice crust. The European Space Agency's JUICE mission is on its way there right now. What Ganymede's magnetic field implies about its interior structure is still being worked out. A human geologist standing on the surface, drilling, sampling, and responding to what the drill actually finds, rather than what the models predicted it would find, changes the quality of the science entirely. And Callisto, the outermost of the 4 Galilean moons, sits almost entirely outside Jupiter's worst radiation belts. It is geologically quiet. It has water ice on the surface. Some researchers have pointed to Callisto as the most practical staging point for human operations in the Jovian system, close enough to Europa and Ganymede to mount crewed excursions, far enough from Jupiter to keep radiation exposure survivable. Compare this to what is happening around Saturn. Titan has a thick nitrogen atmosphere, lakes of liquid methane on its surface, and chemistry happening there that resembles a very cold, very slow version of what Earth's early atmosphere may have looked like. Enceladus is shooting water vapor from cracks in its south pole directly into space, material from its subsurface ocean that a spacecraft could fly through and sample without even landing. The outer solar system is not empty. It is full. And the reason we have not been out there with human crews yet is not lack of interest. It is the math we spent the last 18 sections of this discussion walking through. But here is the real weight of the question. There are 2 futures on offer. In one of them, humans stay in the neighborhood, the Moon, Mars, maybe the asteroid belt, and robots go everywhere else. The robots get better, the data gets richer, and we learn everything there is to learn about Europa's ocean from a distance of 400 million miles. In the other future, humans eventually go themselves. Not because robots have failed, but because there is a difference between exploring a place and being in it, between measuring a world and standing on one. The decision to send humans to the Jovian system is not a scientific decision. It is a civilizational one. It is a statement about how far the definition of home is allowed to extend. Every mission architecture we have ever built for Jupiter has been a choice about what comes next. Pioneer was a test. Voyager was a revelation. Galileo was a commitment. What would a human mission be? The journey to Jupiter is not really about Jupiter at all. It's about what lies in orbit around it, and what the decision to go there would say about what kind of species we intend to be. The answer to how long it would really take us to reach Jupiter is not a single number, and the reason it isn't a single number is the most interesting thing about the question. Here is what the honest range looks like. A robotic spacecraft built for speed and nothing else. No need to slow down, no science instruments to protect, no orbit to enter, can make the trip in about 13 months under ideal conditions. That is what New Horizons did. It was the fastest launch from Earth ever attempted at the time. It flew past Jupiter without braking at all, and it still took over a year. That is the fastest end of the range. The slow end is 6 years. That is what Galileo needed, looping past Venus and Earth twice, just to build up enough speed to reach a planet that was, at its closest, about 365 million miles away. 6 years to cross a distance that light covers in 43 minutes. Both of those numbers are correct. Neither one answers the question. What actually determines the number is a set of choices. Are you stopping or flying past? Stopping costs an enormous amount of fuel. That fuel adds mass. That mass requires more fuel to move. The spiral compounds quickly, and by the time the math settles, you are looking at a spacecraft that takes years longer to arrive just because it needs to brake at the end. Are you launching at the right window? Jupiter's alignment with Earth shifts constantly. Miss the optimal window and the trajectory gets worse. More fuel, more time, or both. Are you carrying humans? Then the math changes entirely, because humans need food and oxygen and medicine and exercise equipment and radiation shielding. And all of that mass adds up to a spacecraft that nothing we have ever built could actually launch in its current form. For a human crew using the propulsion technology that exists right now, the round trip to Jupiter would take somewhere between 6 and 9 years at minimum. That assumes everything works. It assumes no mission extensions, no navigational corrections that burn extra fuel, no delays waiting for the return alignment window to open. 6 to 9 years in deep space, past the protection of Earth's magnetic field, absorbing cosmic radiation the entire way. Astronauts returning from 6-month stints on the International Space Station sometimes need help standing up when they land. Now multiply that by a factor of 10. Nuclear thermal propulsion could change this. If Draco, the joint NASA and DARPA program working on nuclear thermal engines, reaches a flying spacecraft by the late 2020s as planned, and if that technology matures enough to scale up for a crewed mission, the travel time to Jupiter could potentially drop to somewhere around 3 to 4 years each way. That is still an enormous commitment, but it is a different order of commitment than 9 years, And the difference between those two numbers could be the difference between a mission that humans can survive and one that they cannot. More advanced concepts, fusion propulsion, laser sails, nuclear pulse, could push the timeline into months for a crewed mission. The physics allows it. The technology does not exist yet, and none of the programs working toward it are funded at the level that would produce a flying spacecraft within any near-term window. This is worth sitting with. The speed is not forbidden by any law of nature. It is forbidden by the gap between what we have decided to build and what the problem actually requires. Every number in this entire conversation sits at the intersection of two things. On one side is the physics, orbital mechanics, rocket equations, radiation belts, communication delays. That side does not negotiate. The distance to Jupiter is what it is. The energy required to cross it quickly is what it is. On the other side is human ambition, which is the variable. How much are we willing to invest? How much time are we willing to spend developing propulsion systems that don't yet exist? How seriously do we take the moons of Jupiter, Europa's buried ocean, the possibility of something living there, as reasons to go rather than as interesting facts to collect from robotic data streams? The real answer to this question is not 13 months. It is not 6 years. It is a choice that hasn't been made yet. Every timeline attached to a Jupiter mission is a reflection of a decision about how much that destination matters to us. And right now, the honest answer is that we haven't decided it matters enough to build the tools that would get us there in a time frame a human crew could endure. What we have done is send robots. Pioneer made it in 21 months. The Voyagers reshaped everything we knew about the outer solar system in under 2 years. Galileo orbited Jupiter for nearly a decade on a 6-year cruise. Juno is still out there, still returning data, slowly being eaten by radiation that has no equivalent anywhere else our spacecraft have ever been. Each of those missions arrived carrying questions nobody had thought to ask yet, and left with answers that made the questions bigger. On any clear night, if you know where to look, Jupiter is one of the brightest objects in the sky, close enough to see its moons with a pair of binoculars, far enough away that we haven't figured out how to get there in less than a year. And the distance between those two facts is where the real story lives.